Welcome to Go Get It. On request from my few of my subscribers, I am presenting AVL trees today. The prerequisites for this video are trees, BST, that's binary search tree, and some generic terms with respect to trees, say height of a tree. As you are well aware of BST, consider a case as shown here. You can notice here the search efficiency of the tree becomes big O of n due to its degenerate nature. As BST, when you apply the BST on this tree, so what happens? The BST algorithm needs to apply on each and every node of the tree, which violates the basic necessity of a binary search tree, and hence it leads to an efficiency of big O of n. To avoid such situations, researchers named Adelson, Velski and Landis, they defined the concept of height balanced tree, or they are also called as self-balancing binary search tree. So what do you mean by height balanced tree or a self-balancing binary search tree? So as I told you that the AVL trees, which is named after its inventors, that is A, V and L, makes AVL trees. And the most basic important factor to be considered in case of AVL trees is height of two child subtree of any node differ at most by 1. This is very important to be considered, at most by 1. So what does this statement means? Let's see here. Consider this tree, this being the root node, and this had the child, left hand side child and the right hand side child. Now what is the height of two child subtree of any node differ at most by 1? Now what does this mean? Let's see. So this root node or this node, this specific node, has two children at his left side and one children on the right hand side. So there is something called balance factor. So generally some people consider number of nodes, or some consider number of edges. So we'll consider the number of edges here. So to calculate the height of this tree or the node marked node, so what happens here? The height of this node is calculated based on the last distance from the last node. So to reach the last node from this root node, how many edges comes in picture? So you can see to reach this node, it has 1 and 2 edges. So the height of this tree or this node on the left hand side is 2. Similarly on the right hand side, if you see, the height is 1. So height of two child subtree of any node differ at most by 1. That means 2 minus 1 gives you 1 for this specific node. So the same principle is applicable for all the nodes. So in such case, you can see for this specific node, this node is under consideration as of now. So for this node, on the left hand side you have only one thing, and on the right hand side we have nothing. So it becomes plus 1. I'm mentioning it as a plus or minus because if nothing is there on the left hand side but on the right hand side one node is there, then it will become minus 1. And similarly for this node, for this specific node, we don't have left child or the right child, then it becomes 0. So that satisfies the basic principle of an AVL tree, because the height of any subtree of any node differs at most by 1. So let's see one more example where you can notice that it violates the basic principle of an AVL tree. So here you can see that this particular root node has a height of plus 2. How? 1, 2 and 3. To reach the last node from the root node, we have 3 edges in picture. So this becomes 3 and this is 1. So 3 minus 1 becomes plus 2. This become again plus 2. How? 1, 2, here 0. So 2 minus 0 gives you 2. This becomes 0. So in this case, this complete tree or this node you can say it violates the condition mentioned here. So that is the basic principle of AVL tree, and AVL tree revolves around this concept only. Now there are certain terminologies associated with AVL trees. Before that, you can see here, this is balanced tree and this is unbalanced. So as I told you, there is something called balance factor, which is calculated as height of a left subtree minus height of a right subtree. So in the AVL tree algorithm, you can see that this balance factor is calculated on every iteration. Now there are certain terminologies associated with AVL trees, that are left-left imbalance, right-right imbalance, right-left imbalance, and left-right imbalance. Now what does this imbalance concept in AVL trees? You can consider the given tree here. Here I have already mentioned the height difference, and consider this node is added extra. So you can say here that for this node A, we have a height difference or the balance factor of 2. How? 3 minus 1 gives you 2. Similarly, plus 1 plus 1. So if you can see here, or if you recall the basic principle behind the AVL tree, you can notice here that it violates the principle. Now where does it violate? It violates at the root node itself. These does not violate. So we have to do this. This is called as left imbalance. Why left imbalance? So as I told you, this inserted node was not there initially, it was inserted later. So initially, if you consider, we had the tree till this level. So if you consider, if you don't consider this node, so you can say that 2 minus 1 gives you 1, and this was satisfying, this complete tree till this level was satisfying the AVL tree property. But as soon as I inserted one node on the left hand child or the left hand subtree of the root node, then the imbalance occurs in the tree at the root node. So as you have entered or inserted the child or the extra node on the left hand side, so that's why it is called as left imbalance, because it is on the left hand side. So to avoid this, or to come over of this situation, so how does the AVL tree algorithm works? So in such situations, we have to do right rotation. So this symbol shows that we will rotate this B node on the right direction. So let's see what happens. So first of all, B moves completely with all its child. So you can notice the movement or the animation, whatever you can see right now. So you can see that B has rotated right hand side, and it has disconnected its one of child which was on the right hand side, and it will go and it will join on the A. And this is the balanced tree. So you can notice here that this B node has 1 and 2 height, and here also 2. So 2 minus 2 becomes 0, and all other nodes are also balanced. So that's how for left imbalance case we have right rotation. Similarly, we have right imbalance. So in right imbalance, again I am going to insert a extra node on the right hand side or the right subtree of the root node. So you can see here again the imbalance occurs. So we will do a left rotation here. So in case of right imbalance, we have left rotation. So on left rotation, how does it work? This complete B will move on the left hand rotation. So what happens? It will keep its right hand child as it is, but it will get disconnected from its left hand child. And this left hand child, as it is a part of B and on the left hand side, so definitely it is gonna join on its left hand subtree. So that's what is happening. So B has been moved to the root side. This has pushed A down. AR remains same as a left hand child of A. BL being left hand side node of B, so this will connect to A because it is on the right hand side. That means it is simultaneously satisfying the binary search property also. BL being highest or greater than A, it is on the right hand side, and but it is lesser than B, that's why it is on the left hand side of B, and that's how we achieve the AVL tree property. So you can notice here the height balance property is maintained here. Next terminology used here is right left imbalance. So in right left imbalance, what does this mean, right left imbalance? So here you can see that the imbalance factor or the balance factor has become 2 for this node. How? If you see here, the newly inserted node was pushed on the right hand side and then on the left hand side of the affected node. So how does it work? This is the right hand side, and on the right, if you come on the right hand side, you can notice that the child has been inserted on the left hand subtree. So that's why it is called as right left imbalance. But in case of right left imbalance, there is certain complexity with respect to rotations. So to achieve right left imbalance, first of all we need to do a left rotation. So that gives you this kind of tree. This is general people, like people will think initially that if I rotate B on the left hand side, I'll get the balanced binary tree, but this is not so. So as you can see, I have rotated B on the left hand side, but again the situation remains the same. B has 1 2 3, 3 minus 1 2. Again the root node has the same balance factor as 2, which violates the AVL tree principle. So how does right left imbalance work? Consider the same tree again. So now what is happening, you can insert any child on the left hand side. That means I have inserted CL or CR, either of them you can insert, or any case you can consider here, but it is right left imbalance for this node. So right left, so that's how right left imbalance comes. Now what we will do here, we will do the affected area first of all. So here the green box, we will consider the green box items first. So we have here B, C, CLR and BR. So you can notice here, if we rotate C on the right rotation, so what will happen, it will give you this kind of structure. As we discussed earlier also, that right rotation, how does it work? So this complete has revised to this thing. Now we had this original tree, A on the root and AR on the right left hand side. So we'll completely, this complete set has been has to be pushed to as a right hand child of A. Now this structure occurred after the right rotation. Now we will do a left rotation, because now the imbalance is on the right hand side. So we will do a right rotation. Sorry, it should be a left rotation as the imbalance is towards the right. So on rotation of taking a left rotation, we will get such a structure. So this C has pushed this A. This A will keep AR as it is, as its left child, but being CL, being greater than A but lesser than C, it will be on the right hand side of A but left hand side of C, left hand subtree of the C. So you can see here this structure again, this remains same, this remains same. The only difference being this will push A and CL becomes the right hand child of A. And again, if you calculate here, this complete tree is a balanced tree. Every node has a 0 balance factor. Similarly works the left right imbalance. Here the imbalance or the imbalance occurs on the left and right side. So that's why the name is left right imbalance. Similar way as the right left imbalance, we will consider the factor where the inserted nodes have been added, or the area. So this gives us this part. We'll do a left rotation, as the right hand side, it is left, it is right, where the weight on the right hand subtree is more, that's why we'll do a left rotation. So on doing a left rotation, we will achieve with this kind of structure. So again, we had the principal or the main root as like this, and we'll join the complete set. Now again, you can see here we have left side imbalance, or the weight is towards the left hand side, so we'll do a right rotation on C. So on doing the right rotation on C, again we'll get the same kind of balanced tree. So these were the 4 terminologies associated with AVL tree. Now let's consider an example where we will be creating an AVL tree using the nodes. These are the nodes which need to be inserted into a AVL tree. So first of all comes in 21. So this is being the root node, no action needs to take. We have 26. So you can notice here that simultaneously it is following the binary search property. So 26 being greater than 21, it is on the right hand side. Next item is 30. 30 being greater than 21, 26, so it comes on the right hand side, and 30. Now how AVL tree works? AVL tree works with every node, it applies the algorithm. So as soon as it comes on 21, as soon as 21 comes into picture, it will apply the AVL algorithm and it will check the balance factor of 21 or the node in the picture. So you can see here 21 was, when it was inserted, it has 0. When 26 got inserted, we had a height of 21 as -1 and 26 as your 0, and then 30 is got inserted. So as soon as 30th got inserted, so the algorithm determines that the root node or the 21 has a negative or -2 as balance factor, which violates the AVL tree principle. So what does it do? As we discussed earlier, this is the case of right imbalance, because due to insertion of 30, the imbalance occurred in 21. So we will do a left rotation here. So due to left rotation, what it can be? So 26 will will push 21 on the right hand side, and 30 will remain same. So you can see the structure. 21 on the left hand side, that means 26 has pushed 21 on the left due to left rotation. So this was right imbalance. Now next item we have 9. So we will add 9 being lesser than 21, 26 and 21. So it will be a left child of 21. Next item is 4. So again, before I mentioned, you would have judged that as soon as you entered the 4 or inserted the 4 into the tree, it has created a imbalance in the tree for 26. How? Not only 26, you can see it for 21 also. Now the question arises, how? So you can see for 20, say for example for 4 we have 0, for 9 we have 1, the balance factor, and for 21 we have 2 minus 0. So the difference of left subtree and right subtree for 21 is 2. So this leads to violation of AVL principle. So what we need to do? We need to do as it is a left imbalance, we will do a right rotation. So as you would have guessed as of by now, 9 will move 21 on the right hand side, and 4 will remain as it is attached to 9. So the structure becomes like this. Now it is balanced because 26 is balanced, 9 is balanced, 30 is always 0, these two are always 0. Now next element to be inserted is 14. 14 is inserted, greater than 9, so but lesser than 21. So again the imbalance occurs due to insertion of 14. This is left and on the right. So what kind of imbalance this is? This is left-right imbalance, and imbalance occurs on the root node. So this is called as left-right imbalance. So we'll do a left rotation here, being as the it is a right imbalance. If you can consider some node here, so it will lead to a right imbalance. So So it will give you a result like this. So what we have done here, we have moved 21 to child, I mean we are pushing 9 with the help of 21 due to left rotation, and there is null on the right hand side of 21, so it is empty, and 14 will disconnect from 21, but it is greater than 9 but it is lesser than 21, that's why 14 is on the right hand side. So before this you can see 1, 2, 3, still the imbalance occurs as it is a left right imbalance. So we will do first a left rotation and then the right rotation. So we'll do the right rotation on 21. So as you would have guessed right by now, 21 will push 26 and this will remain same. The only thing or the difference will be this. So this will be the final result of this left right rotation. So next element to be inserted is 28, which will be on the left hand side of 30, being greater than 21 and 26. So again the case arise here is left right imbalance. My mistake, it is right left imbalance. Now you would have considered, now basically if you see here, you will consider that I'll remove or I'll push 30 and the structure will becomes like this. So 30 will push 26 on the right hand side, and 28 being left of 30 but greater than 26 on the right hand side. But this is completely wrong, because if you see, this structure has again resulted the same kind of structure. So this is completely wrong. This assumption is completely wrong. So we have to do a right rotation on the right subtree. So what we have done, we did a right rotation on 28 and we have come to a structure like this. So this was right rotation and again left rotation. So left rotation will push 26 and 30 will remain attached to 28 on the right hand side and 26 will move to this. So this will lead to such a structure. Now this complete structure will be attached to 21 as a right hand side child. So you can see here the reconstructed tree. Now next element to be inserted is 18. There is there any imbalance? I don't think. 1, 2, 3 minus 2. No, there is no imbalance. We'll insert the next element 15. So as soon as we insert 15, you can notice here 1, 2, 3, 4. The height for 21 to reach 51 is 4. 4 minus 2 gives you 2. So again a height imbalance occurs. Now what kind of height imbalance it is? Left right imbalance. So again the same funda or the concept applies here. We will consider this complete area 14, 18 and 15. We'll revolve 15 first, and then whatever structure appears, we will get a right skewed tree, and ultimately we'll get a tree structure like 15 will be the root node and 14 and 18 being the left and right respectively. So this was similar to the previous example. Again you can notice here 1, 2, 3. So the height balance on every iteration is calculated, and it is the AVL tree's job is to maintain the height at most by 1, height difference or the balance factor at most by 1. Next element inserted is 10. So 10 has been inserted. So 1, 2, 3, 4, 4 minus 2, again imbalance occurs. So due to this imbalance, what happens? Same way 14, so as it is it has created the imbalance on this child, will do a right left imbalance. So first we will move 14, we'll do a right rotation on 14, so it will lead to this structure, and again we'll do a left rotation on 14 as the 14 being the root node. So what happens here, you will get a structure like this. 21 remains same, right hand side remains same, the only difference occurs is here. So I hope I was able to clear the concept of AVL tree and all the rotations, 4 kinds of rotations associated with AVL tree. So I would keep the rest of the insertion as a practice for my listeners. So the final result of this AVL tree insertion will be kind of this kind of structure. So this is, you can see there here that all the nodes are following, or this is following the AVL tree principle. So every node is balanced, or the balance factor is max 1, or here I can see for this it is 0, for this it is 0, for this it is 0, 0, this complete is 0, for this it is -1, for this it is 0, for this it is 0. So that's how AVL tree works. Thanks for listening. Subscribe for more videos. And there is one request for my subscribers here. As the exams are approaching, I would really appreciate if you guys give me your request, or inbox me your whatever subject you need to learn from Go Get IT. Thanks a lot. Thanks for listening.